So, moving on, I'd like to reacquaint you with Steve Mansour. Since I last saw him, he is Dr. Steve Mansour, so congratulations on that. And Steve is one of these rare and valuable people who straddle the gap between academia and commerce. He works, he's associated with the University of Scranton and Carlisle group. So, Steve.
All right, my talk here is on taming statistics with limited domain operators. I got the title actually from a talk that Ken Iverson gave a number of years ago, and it was called Taming Mathematics. And basically, he was complaining about mathematical notation. So you had superscripts, you had subscripts, functional notation was inconsistent, and various things like that. And I've been teaching statistics at the University of Scranton for about 6-7 years now, and I've been looking at some inconsistencies and problems with statistics and some statistical software packages. And so that kind of gave me the idea for this talk. Also, we've been developing in my business career, programming career, I work with the Carlisle group, and we've been developing a statistical package for their software to go with their database. And so we use Acre for that, so I just wanted to give a little heads up to the Acre guys as well. But anyway, I decided to develop a sort of a student version of this statistical package that I'm working on, and so that kind of led to this talk. Why another statistical package? There are lots of packages out there. We have Minitab. I use that in teaching. There's R, and I know R works with Dyalog APL. Excel has a lot of statistical programs, and SPSS, among others. Here, I looked at Excel, and Excel has about 87 statistical functions. There's a lot of them out there, and 6 of them, I just took this at random, involve the t distribution alone. So the t distribution, and they used to stick them together like T, I, and V. They started putting dots in between the names of the functions, I guess, to make them more readable and to show how they're related. R has, for each statistical distribution, they have like 4 different functions and so just for distributions alone, they have about 80 different functions. So there's lots of functions out there. And so the idea for taming statistics is to kind of reduce the number of functions. Now, APL is pretty good at that, because if you look at, for instance, inner product, you can plus dot times or and dot equals. You can do lots of different things with a lot of constructions in APL. What does APL have that other statistical packages don't? We have defined operators, and I want to mention that operators are very useful. I've noticed that Dyalog likes to develop new operators for various. They've got a lot of new operators out there, and I've come up with some operators for statistics. So I want to show how we can exploit operators to reduce the number of functions. So let's look at an example. How about planning next year's user meeting? All right, I just, I think typically the attendance was about 100. I think, what is it, like 80, and it's 110 last year, and it's about 110. So we got about, let's say we have about 100 delegates every, typical attendance with a standard deviation of about 20, okay? So I just picked these numbers out of the hat. They're just nice round numbers to work with, but this is just for the purpose of an example. Let's assume that next year's conference center can support up to 130 delegates, just as an example. What are the chances that we will exceed next year's capacity. Okay, so I want you to think about that. Okay, how would we go about doing that using statistics? Well, let's see how to do this in Excel. Excel has a function called norm.dist, which calculates the bell-shaped curve, the normal distribution. And the first, it takes 4 arguments. The first one is the number. The second one is the mean. The third one is the standard deviation. The third one says, is this a density or a cumulative distribution? So you give it all that information. And that, of course, that gives you the probability that you have less than 130. So you have to subtract that result from 1, because we want to know what's the probability we have more than 130. Okay, all well and good. But I want to be able to do this in APL. And so I actually have written functions to do this, but I found out that you can do it in R as well. Okay, and so if you want to do this in R, you have to use the R connect workspace, and you have to, first of all, you have to make a call to R, and let's see. So this is the R execute function. This is the name of the R function, pnorm, which is the normal distribution. The prefix P means that that it's a cumulative distribution. And you can give it up to 4 arguments, and they're kind of in the same order as they were in Excel. This 0 says that it's an upper tail. So 1 would mean lower tail, and 0 would mean upper tail. And when you get the result out, I guess you have to put a plus there to make it an explicit result. It's a tacit result or something. So, shy result, right. So I have to do that. So that's how I would do it in R. Well, wouldn't it be nice if you could just enter something like that? Just say 120, the mean and standard deviation, normal probability greater than 130. I think that reads more English-like. Well, let me put some syntax in there and see that if I were to put parens around normal and greater than, what does that look like? It looks like an operator, okay? This is your operator, this is your left operand, this is your right operand. And this is the left argument are the parameters, and the right argument would be the value that you're interested in. So that kind of gave me a sort of a brainstorm. I thought, why not use operators for other statistical things as well? So here are some other examples. I use color coding, syntax coloring, for data in green, functions in red, and operators in blue. So if I wanted to use the standard normal probability, I can leave off the left argument. This is the standard normal with a 0 mean and a standard deviation of 1. And I could just do something like that. And if I want to, I could also do probability between. The right operand could be a function I define called between, and give it two items. What's the probability that we get between 100 and 130 delegates next year, for example? We can use discrete distributions like binomial probabilities. Critical value, for example, if you need to look up stuff in tables, the t distribution is one distribution where you want to get the probability that the critical value is less than 5% of all other values. So I chose that notation there. Here's you can also generate random variables for simulation. So if I want to generate 5 chi-square random variables, no, I want a chi-square random variable with 5 degrees of freedom, and I want to generate 13 random variables from that distribution, I can use that notation. You can see that some of these are dyadic operators, and some of these are monadic operators. And you can do inferential statistics such as confidence intervals and hypothesis testing as well. And here's comparing two groups. And you can also get theoretical values. What's the theoretical variance for a binomial distribution with n equals 5, p equals 0.2. So there's a whole bunch of things you can do. And so that's what that's what brought about this whole concept. Now, I wanted to mention that statistics deals primarily with three families of functions. The first family is called a summary function. I'll talk about these in a little more detail. And these are used primarily for descriptive statistics. Probability distributions, we have a lot of probability distributions that are used to model various natural phenomena. And so we'll take a look at those. That's the second type of, second family of functions. And finally, relational functions. And so these are three classifications of functions. And so let's take a look at summary functions. If anybody, I'm assuming most people are somewhat familiar with statistics. And so basically, a summary function basically takes a list of values and it compresses them into a single value. So typically you take a vector and you compress it into a scalar. And structurally, these summary functions are equivalent to g/, where g is a scalar function and the right argument is a simple numeric vector. Okay? And so if you do +/, you take a vector, compress it into a scalar. So a statistic basically is a summary function of a sample. A parameter is a summary function of a population. So for some examples from statistics, you can measure the central tendency of a data set, which is the mean, the median, or the mode. The mode is the most common value. The median is the value right in the center. You can look at measures of spread, variance, standard deviation. These are some various measures of spread, measures of position, percentiles, the max reduction, min reduction, or measures of shape. So these are typically values that would be considered summary functions. Probability distributions. These are functions, they're defined naturally in, there are two types of probability distributions. They're discrete and continuous. And they are defined in a natural way. The probability mass function for discrete, and the continuous is what we call the density function. Now, the natural way of defining these functions is not the most useful. So the function, when it's just written out in its native way, will produce the natural result. However, what we want to do is apply an operator to it to give it a useful result. The density function for continuous distributions is not, it's the height of the bell curve, for example. And that's not terribly useful. What's useful is the probability that it's less than or greater than something. Probability distributions all have the same general syntax. The left argument is a list of parameters, such as mean and standard deviation for the normal distribution. The right argument can be any value taken on by the distribution, and basically the distributions are scalar with respect to the right argument. So that's the way I've defined them. So that the right argument can be basically any structure, and basically it applies the function to each item of the right argument. Here are some examples of some discrete probability distributions. If you've taken a statistics course, you should be somewhat familiar with them. And here are some examples of continuous distributions and the list of the parameters. And so I've implemented all of these in the system. The third piece, the third type of function that we use often in statistics are the relational functions. Basically, I mean, most of you already know this, they're dyadic functions whose range is 0, 1. So they give a result of true or false. And these are some typical examples. Most of them are primitives, but if you want to write your own, I wrote one called between that gives you the value. If it's between two values, it will give you a 1. Otherwise, it'll give you a 0. Now, the talk was called limit. I coined the term limited domain operators. And what do I mean by this? Well, if I'm going to create an operator, it doesn't work on just any function. It only works on functions of a certain family. So if I limit the domain of the operator, then it's not going to blow up. I mean, if you want to use the wrong function on it, be my guest, but it's going to blow up. So I'm limiting the domain of these. You'll kind of get some kind of domain error. I guess you can use I'm assuming you can use the term domain for functions. The domain of an operator would be a list of functions. So I'm kind of using that term loosely. So the domain of the function would be limited. The domain of the operator would be limited to a set of functions of a certain classification. And so I can, and if it's a dyadic operator, the left operand would have a certain domain, and the right argument would have may have a different domain, but the same family of functions. So these are the limited domain operators that I came up with. The first one was probability. The left operand is always a statistical distribution. The right operand is a relation. So it can be equals, less than, greater than, less than or equal to, and so on. And they all kind of follow that form. Critical value, pretty much the same thing. The critical value is basically the inverse of the probability function. And basically you give it a probability and it's going to give you the value of the distribution that corresponds to that probability. If you wanted to do a confidence interval, let's say you want to do a confidence interval for a mean of a sample, or the confidence interval for the mean of a distribution, but you use a sample to get it, you would use a summary function as the left operand, and it's a monadic, so you don't have a right argument, right operand. Hypothesis testing is whenever I teach statistics, there's lots of different hypothesis tests that come out, and those hypothesis tests, there's so many different flavors of them, it explodes, because you can do hypothesis tests on means, on variances, on proportions, and they can be the hypothesis can be, is the value equal to something, greater than or equal to something, or less than or equal to something. So it starts to explode. So we can hypothesis testing, we can give it a summary on the left and a relation on the right. And so again, this is a dyadic operator. I'm not going to talk about this. I'm not going to show you an example of this, but you can do goodnessOfFit tests if some data, does it fit a certain distribution. The random variable, you can do simulations by generating random variables from any distribution. In APL, we can do it from the uniform distribution, and I noticed that you can also do it for the 0-1 continuous distribution by using (0) now. But I want to expand that to any of these distributions, so we can do that with the random variable operator. And theoretical and running, these are some other ones that I put out there. So we can take this whole idea of operators and do lots of different stuff in statistics. I want to emphasize that this talk is about design and syntax, not necessarily implementation. I did implement these. I wrote everything in APL, and it took a long time to do it, particularly some of the more esoteric distributions like the T and F distributions. I did have a little problem doing it. So I experimented with, I started looking into R, see what R can do, because I don't want to just reinvent the wheel. If R can do it better, let R do it. So I don't care how it's done. So I actually rewrote some of these functions and just did a call to R. But I didn't really like the syntax of R so much. I wanted to use this this scheme in order to call functions in R. So I'm really trying to emphasize that the most important thing is the correct nomenclature for what should I name each of these functions and operators, and does the syntax make sense? And I would like to get some feedback about how this thing is done. So I'm really not going to show any examples of code. I'm going to show how you can call these functions, but I'm not going to show any code because that's not really the point of what I'm doing here. One other thing I just want to mention in passing is that particularly when you're doing hypothesis testing, sometimes you can give it you can work with raw data. Sometimes you want to, and other packages do this, sometimes you want to just give it summary data. So you can represent data in three ways. Just a vector of the raw data, or you can represent it with a frequency distribution, which is just a matrix which shows the values on the left and the probabilities on the right, or with summary statistics, so sample size, mean, and variance, for example. The first one is a vector, the second one is a matrix. The third one we call a property space, but really it's a namespace with some variables in it, variable names in it. So that's how we do that. But they all should be interchangeable when you call the operator. You can pass any one of those three things in, and they represent a data set. So if I have a data set D, and I can generate a frequency matrix. And here, the mean and variance of D, these are summary functions. And here I can create a property space and just shove in the count, mean, and variance into the property space. And so those three things, D, FT, and PS, are different structures, but they represent the same thing. Well, implementation, I've created two workspaces. One is called Taming Statistics, which is just the functions that I wrote, and then I've created an R version of it. So I'm going to show you the R version. So let me show you. First of all, you wanted to find out. I didn't give you the result of what's the probability that we get more than 130 delegates next year, given the input. We don't know what that probability is, but so it's about almost 7% probability of that happening. And that's using the R notation. And here I'm using, that's the R syntax. But my function obviously gives the same result. And with the parens, which are redundant. Now, supposing we want to get a bigger venue, so we want to find out what's the probability that we will turn people away less than 1% of the time. And in this case, we use the critical value operator, and it says we need 146.53, 147, so we'd need a larger haul for that. So these are just some of the problems that you can solve in here. Simulate the attendance at the next 10 meetings. So I can generate a random variable and just simulate the attendance. So these are just some things. And what's the mean attendance? I can generate a confidence interval for the mean attendance. So it between 86 and 110, would be the average attendance. I can do like coin tosses. What's the probability of getting 3 heads and 5 coin tosses? guess I could make that big. Okay, let's see. What's the probability of getting fewer than 3 heads? I can apply the operator to a vector, 0, 1, 2, and 3, or 0, 1, and 2, right? Because we're in origin 0. So I can do that, and I can sum those up if I want the probability, but I can just do it directly by saying, yeah, I can sum it up. That would be 50%, but by using the less than sign, I can just do it directly without having to do an extra sum reduction. So these are the kinds of things that can be done. How about at least one head, for example? Also, like tables, like that you need to, instead of looking up stuff in tables, like I can generate a critical value of the t-distribution for various upper tail probabilities. Now notice that there's lots of inconsistencies in other packages, because the normal distribution, they usually use lower tail probabilities, but the t and the f distributions, the tables are all set up for upper tail probabilities. And I always get, it gets confusing, but if you're using operators, you just give it the right symbol, less than or greater than, and it will give you the tail that you want. What about an F table? And F table is generally two-dimensional. Here I'm using the the monadic commute operator to show degrees of freedom from 1 to 5 for 5% upper tail F distribution. So you can generate an F table if you want. And here I'm just doing the frequency stuff that I was working on, mean and variance. I showed you this before. So I can generate a confidence interval from a property space. I can generate a hypothesis test. I can say, is the mean equal to 2.5, and it gives me the probability given the data that I have. Generally, this is what we call a p-value. So when I do a hypothesis test, the result is a p-value. It tells you what's the probability you got the result you did given the data. So that's an example of D is a data set. And I can get the same result, or a very close result, that using there is a little round off in the mean and variance calculation, so that when you use the summary data, your answer is slightly different, but generally it should give you the same result.
I think you missed the 4 on the PS.variance.
Did I?
3 4s in the previous one.
Oh, maybe that was it. Yeah, I think I just typed it in. That may well have done it. So I could type in PS.variance gets, what, 2.5444? Was it? And let's see if that, well, got closer. Yeah. I truncated the numbers to 5 decimal places instead of 10, so there's probably some rounding going on there too. But anyway, again, it's showing interchangeability of various data representations. And, well, can we do graphics? Well, I've been playing around with this, and so I just wanted to kind of show you this. You can generate a normal graph, and basically you can do the left tail, and you can say, well, or you can simply type it in. What's if the left tail is 1.2, and it will give you, it will kind of give it to you. If you change the direction from greater than or equal to less than or equal, it'll change it to the upper tail. So I've been kind of playing around with the graphics. Still needs some work, but generally that's what I have. So I can entertain questions now.
First, I have a comment.
Yes.
Really nice stuff.
Thank you.
And a question that's almost equally simple. When you ask for confidence interval, where do you put the parameter for alpha?
Oh, that's an optional left argument.
Oh,
I didn't actually, I'm assuming the default is 95% confidence interval, but if you put in, you can give it a left argument because it's a monadic operator that, yeah, I can even show you. So I could say, so basically if I say confidence, I have to give it the operator mean, confidence interval D. And if I can say, that's the same as a 95%. So if I want a 99%, I would just give it a left argument. If there's no left argument, it assumes 95%.
and it's always in percent.
Yes, I could change it to. I'm debating whether to leave it in percent or make it 0.95. You know, that's if I can get feedback on that, I'd be happy. You know. Okay. Any other questions?
A question about how easy it would be to extend this sort of thing. You can take as the right argument to some of these functions descriptions of the distribution or examples from the samples from the distribution and calculate things from it. Have you thought about using that ability to do an arithmetic of distributions? In other words, I have a normal distribution of such and such mean and such variance. I have a Levy distribution of such and such mean and such variance. And what returns is some kind of convolution that describes the sum of those two distributions that you can then run through the rest of the...
Oh, in other words, kind of write your own distributions.
Right,
I mean,
it's sort of an arithmetic
distribution.
Right.
I've thought about that. I've thought about user-defined distributions, and I haven't really done anything with it. I've just been creating them, but that's certainly something that we could do. I'm sure we could figure out a way to do it. But that's a good idea.
Okay. Are you using the R version to test the APL code?
We we're actually incorporating the same scheme into the CAS system, the Carlisle database that we're doing, and we're using R to test. We've got R in those test cases, so I'm testing them there. I haven't really used it on these light. This is sort of statistics light because this is for students mainly. We have a much more sophisticated version of it in our Carlisle group software, which is basically for much larger data sets and stuff like that, and it does more stuff. It does like this, the hypothesis testing puts out more information than just the p-value, but we have structures that the output is different structures and things like that. So I don't have that sophistication here, so it's a slightly different version. But I am using R to test the other versions just to make sure. There are some problems with the T distribution and the F distribution because of some of the algorithms I'm using. Some of the tail values are kind of hard to get. Most of them are pretty good, but I check what's in tables and statistics books is usually pretty good, but stuff that's out in the outer tails and everything, I have a little problem with that. Other questions?
Is this something you would consider making available via GitHub for us all to help you work on it?
I think that would be a good idea. As a matter of fact, I was thinking possibly of
your own branch on the
taking
Dyalog
R Connect. I was thinking might be a good idea to put the functions into R Connect, because then you just load R Connect and you'll get all this. So instead of calling R the way with the omegas in it and everything else, we could just call it through these functions, but you could still do it that way for R functions that we don't have written up or anything. But I would like to do that.
Have you put anything in for Bayesian statistics?
There are some other areas I've been considering, but I haven't actually done that yet. This is basically stuff from the course I teach, and I don't really teach too much with Bayesian statistics, but I have, like there's a regression piece that I have, and hypothesis or ANOVA. Like I've done some work with regression and ANOVA in our main package, and I'm planning to put those in. So I would put, I would like to put as much in it as I could, but it just depends on how much time I have to do it. But any suggestions that you have, if you could email me and tell me you'd like to see this in the package, I would consider doing it.
Thank you, Steve.
Okay.
Thank you.